First off, I'd like to apologize if I seem to be speaking really fast. I've had a lot of caffeine this morning. I'm a developer by nature, so I'm usually up late programming. So to get up this early, I needed a lot of caffeine. Okay, I was asked to give a talk on what we are internally working on. It's known as MapiHttp. It's sort of a replacement for Mapi over RPC, or RPC over HTTP. Mapi obviously is the messaging API that is used on the client. It's how Outlook interacts with Exchange. That typically the transport underneath has been historically always RPC. Most recently, or a couple releases ago, we added RPC over HTTP for remoting across the internet. And in Exchange 2013, we standardized on RPC over HTTP more for internal architectural reasons because TCP transport wasn't routable through our multi-tiered system. But with that, I guess I could go to the next slide. What is MapiHttp? It's basically a transport replacement for RPC over HTTP between Outlook and Exchange. It conforms to HTTP 1.1 protocol specification, and it's based on HTTPS. We do not have a version that is not encrypted. And it uses all just post verbs, so it's very familiar. It should be able to go through any sort of networking device out on the internet. It's just standard web traffic. It is connectionless, but it still maintains statefulness because all of the, if you're familiar with the RPC over HTTP and the way we built ROPS and address book and mailbox access, it requires you to connect, establish a session, and then issue subsequent requests or RPC calls on that context. So we've kept the same premise here. You still can create a context and then still access it, but you're using separate HTTP requests rather than in the world of RPC over HTTP where it's very long-lived, a single RPC request going in and a single RPC request or HTTP request going in and one going out. So why do we want to do MapiHttp? We hear a lot from people. Why can I access email through the browser or my phone, but Outlook is stuck trying to connect? Architecturally, the way the transports work, even though it's RPC over HTTP, it flows a very different path through Exchange, into Exchange, through our multi-tiered system. It's very, very different. There's a lot of complexities there because we've built the protocol on top of RPC over HTTP, which is an actual Windows OS component. It wasn't designed and built by Exchange, but it was built by the Windows team, and they kind of control the actual protocol and how it works, and there's some complexities there. It didn't seem to scale well with our Exchange 2013 environment. I mean, it works fine, but there's some limitations, especially if you're having issues where your backends are failing over and the client has to reconnect, and there's some timing issues there where different front-end servers might think a mailbox is somewhere else, and it routes the in and out channels separately. So what we wanted to do is, if we wanted to make a system where if OA works, shouldn't Outlook? Outlook should always work. If you could access your mail through a browser, hey, Outlook is just a client. It should be able to access your mail just like a browser would. So I thought about it for a while, and I tried to come up with what's something that kind of explains what Mapi over HTTP kind of means to me, and this is kind of what I came up with. So by reducing the protocol complexity and adhering to internet standards, the routing of requests across network devices and handling of Outlook requests within the Exchange multi-tiered ecosystem is now architecturally equivalent to OA and EWS from an HTTP transport perspective. So when it comes into the Exchange system, it's being routed and it's being transmitted to the mailbox server on the back end, just like it would for any of the other HTTP protocols. So the goal of MapiHttp was obviously to reduce the complexity of the protocol. There's no inner and outer channels that RPC over HTTP has. There's no dual channel authentication. There's no paired in and out channels. The server doesn't have to keep track of this channel, the in channel, the out channel have to land on the same server to be able to make communication work. There's no complex algorithms to make sure that those paired connections landed on the same back end and are processing. We don't have any infinitely long request responses. Now, this has always been kind of problematic when you're, say, on the road, you're in a hotel, they have some strange foreign device that routes traffic, and a lot of these devices will cut you off after a certain period of time if the HTTP request is taking too long. But the way RPC over HTTP was designed was to basically send up a request, and it says, my request size is a meg, or gig, I believe. I think it's a gig. So it's essentially telling the pipe in the middle, I've got a very, very long, infinitely long request. And of course, it just trickles data, and it has this internal ping or keep alive that it trickles across this thing to keep things in the middle going. But we found that sometimes devices aren't too forgiving if the thing takes too long, or if the client doesn't send the ping right away. You can get to the point where the connection just goes stale, and the client still thinks it's connected, the server still thinks the client's connected. The client will pass data up, server doesn't get it, server returns data, client doesn't get it, so it just kind of deadlocks. We also wanted to be able to have kind of more clean transitions. As we move into more of a world where everyone uses laptops and tablets, and they're going from Wi-Fi to wired, or going to multiple Wi-Fi networks, we wanted a system where the connection wasn't really bound to the HTTP connection. In the RPC over HTTP world, when you establish the in and out channels, your context was associated with those actual requests. If those requests were terminated, or if there was a failure, or you unplugged or you turned off your wireless, that just ended it right there. So we wanted the ability to be able to have a protocol where you could create a context on the server, and you could issue requests, and if the client detects that the protocol or the network device is changing, or it's going from one adapter to another, it can just resume on another and not have to reestablish everything. So, and also to allow the ability for short-term hibernation. Like, I have a laptop, I go from meeting to meeting all day, and I hibernate my laptop between meetings, and when I get to the next meeting, I have to open it, and it's got to reconnect, and it's got to establish the in and out channels, and it's got to do all this, and it just takes time. So the idea here is that for short periods of time, we haven't quite determined what short means. It could mean 15 minutes, it could mean 2 hours, where you should be able to hibernate, the client just goes away, but when you resume, your context on the server is still there. And the client just continues where it left off. And also, we needed the ability to be able to support new authentication types. Now, I don't really know what those are, but there's new ones, I guess. From the RPC over HTTP world, the OS kind of did it for us. We would pass in a set of credentials, or just kind of use the context of the user who's authenticated on the machine to establish the connection underneath us. But when we get into two-factor auth and other things like that, it was really the RPC over HTTP, the OS was very kind of rigid. It was really hard to plug in new authentication types there. So this kind of frees us from that, and we're able to now come up with some alternate authentication types. I don't really get into that in this slide because I'm not sure we quite know exactly what that is yet. And also, by having clearly defined protocol expectations and timeouts, what this really means is that the client can expect a certain thing from the server. The client today, when it goes to the RPC layer, I'm making essentially a function call, and the RPC layer serializes all the parameters, packages it up, sends it out over the network, and it's really up to the RPC layer on the client and the RPC layer on the server to negotiate all that. And the client's kind of left, or the Outlook client is kind of left out in the cold, not knowing what's going on. Is the request, did it get to the server? Did it not get to the server? It's being processed. It seems to be taking a while. It hasn't failed. It has no idea, is the server even there? Is the server responding? Is the server doing anything? So we thought about it for a while, and we think we came up with a way that the client will always know where the server is and whether the request is actually being processed. So some might ask, why not rebuild with EWS? MapiHttp is kind of more backwards thinking than it is forward thinking. We're looking to replace RPC over HTTP in the client for existing Outlook clients, so versions 2010 and 2013 through service pack updates. It's not really looked at as kind of going forward with the next release of Outlook, but kind of more backwards looking. And the reason is that we wanted to be able to replace RPC over HTTP with something that was easier to use, but it also has to be able to support the old legacy MAPI architecture on the client. We didn't want to go through a lot of code changes in a service pack. And so basically we want to minimize the source code changes, but keeping the architecturally mostly untouched. So in the MapiHttp world, you're still going to see the EMSMDB functionality and the NSPI functionality, and you're also going to see ROPs. So none of that's really changed above the transport. It's just the transport, the RPC layer, that's being replaced. So here are the existing RPC over HTTP. This is kind of a representation of how it looks. So Outlook today it needs to be able to establish, when it wants to speak to Exchange through RPC over HTTP, it has to create two separate requests, an infinitely long input HTTP request and an infinitely long output HTTP request. Now, both of those requests going through the Exchange front end have to be routed to the same back end. It goes into IIS that's running as part of a Windows component on the back end, which then directs the traffic to the RPC layer in the Exchange backend process to handle traffic. All the gray stuff is OS-dependent stuff. So we're dependent on the version of the OS on the client. We're dependent on the version of the OS on the back end to make sure that all these things work. And believe it or not, even though RPC has been around for quite some time, the Windows team seems to kind of make little changes here and there that sometimes lead to some incompatibilities, and we have to fix them later. But so the idea here is we wanted to simplify this picture. So we're not really, in the classic case with EWS, you send up a request, you get a response. It's simple, it's easy, it's a single HTTP request. You get the data back. There's none of this complexity of something underneath you trying to manage these two sessions, and then if the session goes over the gig, it's got to reestablish new sessions or new connections under you. There's just a lot of complexity there. So what we've done with MapiHttp is we've taken this picture and we've made it this. So now Outlook speaks directly to Exchange on short HTTP request responses. It flows through our front-end array as any other protocol, and it's able to transport, I say ROPs here, but it also does address book, NSPI functionality too. ROPs is more mailbox-specific remote operations. But the idea is that there's no gray. So we're not dependent on the version of the client OS. We're not dependent on the version of the server OS. We're kind of OS independent. Okay, so what does a request look like? This is kind of a request that I captured, I think it was yesterday or the day before. It kind of looks like this. So it starts off, everything's a POST request. All of MapiHttp uses POST. It has the URL. The URL is basically identifies the endpoint. And here it says MapiHttp. So it's going to the Mapi endpoint, but it's speaking to the EMSMDB interface. The mailbox ID is basically what mailbox you're trying to communicate with. The entire URL can be retrieved now through auto-discover. So if you're hitting against a server, you could say, as a client, I support MapiHttp. The server will return you now URLs, and the client would then just use that URL as is. You don't have to come up with what the mailbox ID is, and that's kind of, the URL itself is mostly opaque to the client, other than the fact that it has to understand the HTTPS part and any sort of internal port or anything like that the server might return. But other than that, all the path and the virtual directories and any of the parameters are pretty opaque to the client. You should just pass them up to the server as is. So the client has the ability to specify who it is. Here in this request, we've just standardized on a GUID. It's a way for multiple requests for the server side to do server failure logging. So we could associate two different sessions from the same client. So here, the client is specified by the GUID, and the -5 means it's logical connection 5 on the client. So we can kind of, on this, if we needed to for failure logging or even for debugging, we can group them. All of these requests or these clients are for the same client. It has a request ID. Essentially, every request, I mean, it's required. Every request that comes in has to have a unique ID. It's not truly enforced that it's unique. It's highly suggested that it be unique, but it is a required header that needs to be passed. So the client will start off when it creates a new, trying to establish a new session, it'll assign a new GUID, and it has a counter on the end, so every subsequent request, it just increments that counter. And it's more for server failure logging and client tracing. If there's a problem, the client traces the failure, and we can easily find it on the server. The request type basically says what type of operation are we doing. In the EMS-MDB interface world, everyone might be familiar if you've actually looked at the RPC document, the EC2 connect, the EC2 disconnect, the EC2 RPC, and the EC2 async wait. Now we've kind of changed the names just to kind of clean it up a little bit, so now you have connect, disconnect, execute, and notification wait. The connect allows you to establish a session context with the server. Disconnect, obviously, is the opposite of connected. It just tears down and destroys the session context. Execute allows you to execute ROPS against that session context. And notification wait allows you to issue a request to the server where it's kind of like a hanging get. It hangs on to the request until there's some notification to tell you about, then it completes it. But like what we did in the RPC world, the server only hangs on to it for 5 minutes and completes it. It'll let you know if there's a notification or not, and if there's not, you just issue the request again. And of course, the request data, each of the request types have a different... Joe,
you had a question?
Yes.
Two quick questions. Can a client have multiple concurrent requests open to the servers? Or is only one, one request at a time?
A client can have multiple session contexts and can be issuing a single request to that session context. It can't issue multiple requests to the same session context.
So what happens if the client has to upload a large file, for example, and you want to use like chunk transfer, or first of all, do you use chunk transfer? And if you're uploading or downloading large attachments, does all the other activities stall?
The Outlook client itself has, the way it was designed, even in RPC, it has like in cache mode, it has foreground connections and background connections. It kind of establishes separate session contexts, if you will. For immediate online or the user's doing something, it uses a different session context for that. If it's synchronizing and downloading things in the background, it uses a separate session context. Now, we did use chunk transfer encoding on the response, but not on the upload. Typically, a client downloads a lot more than it uploads. We didn't get into the complexities of doing the chunk transfer coding on upload. We still work within the same, because essentially, from an architectural standpoint, the method calls that we're doing, like the execute, the ROPS, all of the infrastructure of the way ROPS work is it kind of makes an assumption that the maximum output buffer size is 256K. It has a lot of internal assumptions in the product, both on the client and on the server. So we didn't want to go in and completely reinvent ROPS, reinvent streaming. So it still works within that limited space. So if you're downloading things, you're going to get 256K of compressed data in a single call. The client can then issue another request and get the next chunk of data. So it's not like a browser where you just start streaming a large file and it just keeps pumping it down. So it is kind of a request response in between there. But for most things, the client is usually, I would say 99% of the time, it's just synchronizing a single new mail as it arrives in your inbox. And generally, a single email is probably going to be smaller than 256K of compressed data. So what we've seen is it's usually just it makes a request, gets that new mail, and it doesn't need to do subsequent.
You said this is a connectionless session, right? So if for some reason the session context is closed on the server side, how does the client become aware of it? Or if
the client, I'll get into more detail on exactly how the client, how the server tells the client what its session context is and how to make calls on it. But the server is free, obviously, to expire the connection context, or even if the server goes down and comes back up, the client is unaware of it. So it'll issue another request up to the server with its session context that it had. The server looks it up, doesn't find it, or sees that it's been expired, and basically just fails the call back to the client. The client, like it would normally if an RPC connection was broken, just reestablishes the session and follows the same path. But the request data for every request is different, and I didn't really get into explaining the serialized format for all those requests. We are working on documentation for this protocol, and it has all that goodness in it. So the response kind of looks like this. Normally in the MapiHttp, outside of authentication failures, initially when you're establishing a TCP connection or HTTP connection, you'll get the 401 and you authenticate. Now the client, it is connectionless, but the client should probably do a good job of maintaining, keeping the TCP connection open to issue subsequent requests so it doesn't have to keep opening new ones, keep authenticating. Most of the failures are returned in the X response code. So from a MapiHttp perspective, if you get a 0, it means from the initial, the client received your request, it had no problem with it, it was able to parse it, it had no issue with the actual request. So from a protocol transport perspective, your request is good. We do use chunk transfer encoding. We do that because we wanted the ability, most protocols, you issue a request, the server starts processing it, and it can take however long, and you get the results. It doesn't really give the client any sort of warm, fuzzy feeling of, hey, did you even get the request? So we had a lot of issues in RPs over HTTP where the client sends a request, the server never gets it. Some weird internal routing error or whatever. It doesn't get the request. So we wanted to use chunked. And the reason is once the server gets the request, he parses it, he thinks everything's good, he queues it to be processed on some worker thread, but he immediately tells the client by responding to it, because now we're in this chunked world where we could just trickle down things. He can immediately respond to it without having to actually wait for the server to actually process the request. So we're able to quickly acknowledge the request, and if the request is taking a long time on the server, we will send down kind of a pending marker saying, hey, the request is still pending. It's still there.
If the server is already responding the response code, and maybe in the working process he has an error, how will you notify the clients?
The protocol does allow for that, and the next couple slides will answer that specifically. Here's some information. This information was obviously, it's just, the server just returns it back to the client as is. It's what the client passed up, just so the client, if it needed to know, hey, what this response was for. It's more for actually maybe tracing in the middle. So we kind of throw it in the response. This is kind of how the client, or the server tells the client its session context. It's all done through cookies. Now, I just used Mappy context, and I'll explain later what Mappy sequence means, but the Mappy context cookie is kind of the session context. The client grabs onto this cookie. If it wants to make subsequent requests for this session context, it just passes up the cookie back up to the server. Now, the client should just treat all cookies coming from the Exchange subsystem as opaque. It shouldn't expect a cookie of a particular name. It's just whatever cookies it gets, it should just squirrel away, associate with that session context, and then just replay them all back up to the server. And cookies will come back on every request up to the server because the the Mappy sequence cookie does change with every request. Okay. And the response body, obviously, it contains the processing pending and finally the actual response data, and I'll explain what that looks like in a minute. Okay, so transfer encoding chunked. So upon an immediate receipt of the request, the server will send a processing marker back to the client. If the request is taking a long time, it will periodically send a pending marker back to the client along that stream. Asynchronously, it just kind of pushes it out. So the client can expect to always get something from the server in a period of time. We haven't really defined exactly what that period of time will be. Right now, it's every 15 seconds it sends out a pending if the request is taking long. Normally, requests to exchange process on the order of milliseconds, so you'll never actually ever see a pending. The only time you will actually probably see a pending, you're sorting a very big table, or you're calling the notification waiting for notification. In that case, the server hangs on to the request for 5 minutes. You will get a pending every 15 seconds. We haven't really decided if 15 seconds is the right answer. I think EAS uses like 2 minutes. Every 2 minutes it sends something. We might follow suit. But right now it's 15 seconds. So finally, when the server is done processing it, we'll send a done marker followed by any additional headers in the response data. Now, the additional headers is getting to your point. If the server later processes it and has a failure, how would it tell the client? The additional headers, it can also pass down another X response code with a failure. So the client needs to be aware that following the done marker are additional headers before the response data, and it needs to treat those headers like it would have if it received them on the initial response. So the client, if it has expected response markers, it allows the clients to quickly know within 15 seconds or 30 seconds if the communication with the server is just gone. It's gone bad. Okay, so processing pending done. So initially, a response from the server looks like this. And then you will get immediately in the response body, the green stuff is the chunking markers. You'll get a processing string or marker. It just says processing. If it's taking a long time, you'll then get a pending. If it's taking even longer, you'll get another pending. And eventually, when it's done, you will see a done marker followed by any extra headers. I think today it only returns a response code. This one says it was successful. It's another 0, but it could be something else. Followed by the response data for the request. And then, of course, you have to terminate the chunking. So that's kind of how we utilize chunking in this protocol. Now, the client specifically doesn't really understand, it shouldn't really understand processing or pending. It's really just looking for done. Once it sees done, but it's expecting to get something at least every 15 seconds. We don't really call out that the client should expect to see the word processing or expect to see the word pending, because we kind of want to leave it open, because we might want to put something else, or somebody else's server implementation might want to say, it's pending, you're number 5 in the queue of so many, you can maybe, or some debug information. The server has freedom to spit whatever it wants out to the client for debugging purposes to find out why a request is taking too long. But then finally, once it sees done, it should then expect the response. So session context. The client establishes a session context with the mailbox using the X request type of connect for EMSMDB or bind for NSPI. And we kind of left, even though they do the same thing, they both establish a session context, we kept the names different because that's just historically how they were named in these two interfaces. So the session context is returned the cookies, and the client must treat the cookies as opaque. All subsequent MapiHttp requests for the session context must pass back all the cookies. The session context is not bound to a specific HTTP connection and should live beyond a single HTTP request. So the client, it's up to the client to be able to get any cookies that it might get on any response, save them or update them from what the cookies it had previously on the request, and then pass them up to the server on the next request. So the server can destroy the session context if the client, if there is no activity after a period of time. With every request, the server will return an expiration info header. And this really is just the amount of time that your context has to live on the server, that the server will keep it around if you don't communicate with it. So the server requires you to communicate it with it at least once within that period of time to kind of refresh that expiration. Today it's set at 15 minutes, but we haven't really decided what that will be. And it's, we return it to the client, so the client doesn't have to hard code that. It can get that from the server, and it can decide, hey, I need to ping the server or do something to the server. Maybe it could take that value and have it to make sure that it's refreshing it from on the server perspective. So every 7.5, 8 minutes, it should ping the server, just to let the server know, hey, I'm still there too. So the client must issue a request to the server before the session context is expired. The client should make a best effort to destroy the session context with disconnect for EMSMDB or unbind for NSPI. Now, of course, if the server is just going to expire it and destroy it on its own, the client might say, well, I'm just not going to bother. But the server also only allows you to have so many session contexts. And if you don't properly clean them up, you could get in a situation where you're not able to connect because you have too many session contexts. We haven't run into that problem yet. I think the Outlook client is really good about trying to disconnect and clean up. So today, the functionality is very similar to the EMSMDB and NSPI interfaces through the RPC world. You have connect, disconnect, execute, notification, wait. And NSPI, you have bind, unbind, and all the other methods that you can do against the address book. Now, I haven't really talked about ping. Ping is a way to issue a request to your session context where the request body is empty. There is no request body. It's just basically saying, I'm still here. Refresh my session context expiration. So sequencing, that's the other cookie that gets returned to the client. Subsequent request requires passing back a sequence cookie returned on a previous request. This limits the client from issuing multiple requests at the same time. We theorize that in the RPC world, your requests are essentially guaranteed on the server to be dispatched one at a time. It doesn't allow the client to dispatch multiple requests for a given RPC context handle. When we implemented this, we were like, well, you know, somebody theoretically, if they have a session context, they could issue 100 requests all at the same time. So we had to have a way to prevent the client from doing that, and that's more internally, we don't have the ability to be processing multiple ROPs, multiple operations against the same mailbox at the same time. So connect, bind, ping, and notification wait are the only requests which don't really require a sequence cookie. And the reason, I mean, it's understandable connect, you don't have a session context yet, and even bind, and even ping, you need to be able to just asynchronously ping the server. But notification wait was also one where it kind of had to be done out of band, where you need to be listening for notifications while you're doing operations. So that one doesn't require you to pass a sequence cookie. Now, you can pass it up to the server, it's fine. The server will just ignore it. Now, theoretically, you could issue 1 million notification waits all in parallel, but the server just keeps the last one. So if you have one pending and you issue another, it just completes the one that it already has and then hangs on to the new one. So sequencing looks like this. The client passes up a request. It has a sequence. It got a sequence cookie back from a prior request, and it was sequence 14. Now, there's some other junk at the end of this sequence. The server just randomizes a value and puts it here so the client can't guess the next value, because if it's 14, it's probably going to be 15. So it puts some sort of random value on the end of it, so it keeps the client honest. Hey, I have to kind of wait for the previous one to be able to issue another request. So he passes up the sequence cookie on this request. This is an execute request, so the client's trying to issue some ROPs. In the response, he gets back sequence 15. So he then squirrels that away and saves that because he wants to issue another request, and he passes up 15. And I don't know if you noticed, but the client will also update the request ID to the next, it was 132 in the previous slide, now it's 132. So he's issuing another request with this, the updated sequence cookie. And of course, he gets the response for this one, and he gets 16 with some random junk after it. But the client really shouldn't, like I said before, the client really shouldn't be expecting to see certain cookies by name. It should just take all cookies and store them. There's some other stuff here that I've kind of removed from the output just to kind of clean it up. Our middle tier layer adds some cookies and adds some headers and things in there as well, more for debugging and things like that, and also for routing purposes. So here's an example of what a protocol failure would look like. So this is a response to an execute request. You notice it comes back with a 200, but the response code isn't 0, it's 10. Now, all the response codes are all numerical values. In the documentation, it'll explain what they mean, but the value of 10 here means that the session context, we weren't able to find the session context based on the cookie. Essentially, the context is gone. Or maybe it never existed, I don't know. But it couldn't find it, so it returns a response code of 10. There's some additional information. Here's some of the headers that the middle tier adds in there, that the request was actually processed on this back-end server. It flowed through this front-end server. The client could log that for debugging purposes. The response is also chunked, but you'll notice that the content type is HTML. We wanted the ability to give the server the ability to just kind of put whatever it wanted in there to be used for debugging. So the server, on most protocol failures, when the response code isn't 0, is free to put whatever it wants in the response body. This is an example from the Exchange server. It's just kind of spitting out the location of where a particular failure occurred. We were trying to get the session context from the session context cookie and couldn't find it, so we threw an exception, which resulted in the request failing. So that is a quick run-through of MapiHttp. Yes?
So in the request, you're using the post method. The string following the post method, mappy / whatever, is that a given format that all Outlook clients are going to follow that post mappy /
The format is kind of more dictated based on the server. The server can do whatever it wants and put whatever it wants in there. The client should issue an auto-discover request. It'll get the URL. It'll have all that information in there. So different server implementations might have different things in there. It might have a different path. It might have different parameters. The server implementation is kind of free to do what they want. We use mailbox ID. That's kind of the same thing that RPC over HTTP used to route things through our front end. It just logically made sense for us to kind of follow suit to be able to route the request to a given mailbox.
Okay, I have several questions related to the how this Outlook and Exchange new protocols will work together with the filtering proxies. Because we are developing the filtering web proxy, and many clients use it as a reverse proxy for SharePoint and for the Exchange itself, just to prevent the malware and viruses to come to the network. The main question, first, how the client will behave if it will not receive a pending or processing request response during the 15 seconds. It will issue the new request.
Yeah, the client, I'm not quite sure I understood the first part of your question about the web proxy. I know.
So the typical situation in our proxy. So some parts of the proxy, the filtering parts, requires that the data should be partially downloaded, at least maybe 10 kilobyte or whatever, before sending the data to the client itself. So the downloading could take some time, especially if the Exchange server itself doesn't answer. So we are getting the processing, then we are getting the pending, we are getting pending. It's collected everything mostly in the proxy. And answer doesn't come to the client itself, because proxy, filtering part of the proxy, expecting for the more data, just to check them.
In the Exchange server, the way we've implemented it, I think a lot of the underlying TCP stack uses some sort of Nagel algorithm to buffer up stuff, to not send smaller little packets. We explicitly turn that off on the server side. So the initial response with the processing will immediately get kicked out of the server. Now, what's in between, we can't really dictate that, but chunking is a very common method of streaming data across the internet, and I hope devices would adhere to that. At least it does for the browser anyways. But, but I understand your point. If somebody has some device in the middle that might buffer requests, there may be some issue with that.
Okay. So for us, it's very important to get the specification early, so we could prepare at least the special handling for these protocols, early detection of request response between the Outlook and Exchange.
Right.
Okay.
Yeah, the processing pending and done markers are kind of by design in the protocol. The client needs to get them in a kind of as they occur, because there is some timing aspects to the protocol. If the client doesn't see something within a certain period of time, it should assume that there's a problem. Now, the client is kind of free to do what it wants when it receives these failures, but in our protocol documentation, I believe we're going to have recommended things for the client to do. If it doesn't receive something at a certain time, what should it do? A lot of it is, basically the recommendation is to just close that TCP socket, open a new one, and issue the request again. The server may have gotten the request and may have already processed it. That's where the sequence cookie comes in, where the server says, you're kind of giving me something that I've already done, and he rejects it. It'll be a protocol violation. The client will get the failure, and in that case, he then needs to just tear down the session context and open a new one.
Another question about the HTTPS. Does the Outlook, in this case, will use the standard certificate authority that's used by Internet Explorer, for example? Because when the man in the middle is implemented, then we need to upload corresponding certificates, so we could decrypt the traffic. So Outlook will use this standard storage.
Shuri, who's coming up after me, is from the Outlook team, and she's going to talk about MapiHttp from a client perspective. But I think from her perspective, I think she's just using WinHTTP in Windows. It's a pretty standard transport. It's whatever it's using. So I believe that's pretty common with what IE or a browser uses. So
okay. So it's if it's standard, so it will use. Okay. Yeah. I think. Okay. Thank you.
Right.
Any plan to deprecate RPC over HTTP?
Well, RPC over HTTP is obviously going to have to exist for a period of time. We can't, even though we would like to instantly update everybody's machine across the world to use this new, great, wonderful protocol, but that's not realistic. So there will be dual stacks within the Exchange, at least for the on-premise world, and for the data center or Office 365 offering. I believe we will still support it as well for a period of time, but as customers upgrade their clients, we could then, based on usage pattern, we could determine whether we need to continue supporting it or not in that world.
And it will be in Exchange 2013, and for Office, it will be which clients?
The MapiHttp will be available in Exchange 2013. We're not planning to backport it to previous versions of Exchange, but in the client, I believe it will be in a service pack for Outlook 2013 and Outlook 2010. I don't know if there's plans to go farther back than that. I don't know. Nice. This one over
here. Two questions. In the failure description, is that localized for the client?
No, it is not. It may or may not survive this slide. It was something that we initially put in there for our own internal debugging to make it easier for us to understand what the failure meant. We came up with a bunch of different response codes, and the client and the server, sometimes the values meant different things, and we wanted to say, this is kind of what the error meant. We may completely get rid of that and purely go off of a numeric value of what the failure means. But the failure is kind of, internal more for tracing to kind of give an idea of what the failure meant on the server. But a client application should really just be triggering off the number and taking a corrective action based on that.
Also, the responses don't seem to have any length. So if you're building a client and you want to show progress indication, how could you do that?
I think currently today, progress, say when you're syncing data, it's actually done at the ROP layer. It's using our incremental change synchronization infrastructure. It's built up across a bunch of different ROPs. And as you're syncing a folder, it's giving you the serialized message changes and deletes. And within there, there's actually progress information. So the client, from this perspective, wouldn't really change because it's still making calls to the server, getting data, and updating its progress based on the information within the ROPs. But outside of that, you're correct in, say, the NSPI world, or you're accessing the address book, and you're doing a query, and you're asking for a bunch of rows in your address book. The server will just start sending you data. But there is upper maximums. I don't believe we allow anything larger than 256K in a response. So it's not like we'll be streaming megs and megs of data. So I guess it just depends on how fast the connection is. Anything else? The question was, what's the timeline that MapiHttp will be expected? I don't have any actual confirmed dates. I believe we are thinking about scheduling it. I believe there's a client update scheduled sometime in September, somewhere in there. I'm not qualified to make those calls. I don't know. Sometime this year, I think. Or next year. Outlook could comment on that. From the server side, we're ready to go. You know. Okay. Any more questions? Yes.
To the server side, it will be a separate option that should be enabled for the Exchange server. So it will be use MapiHttp, or it will be automatically discovered by the client.
Now, the server has to be able to interoperate with clients that don't support it. So kind of the way this is triggered is when the client issues an auto-discover request to the server, in the request going up, it kind of tells the server, I support Mapi over HTTP. Now, if it's an older server, he doesn't know to look at this and ignores it and just gives back RPC over HTTP information, and the client just goes with it. If the server does understand it, it will return Mapi over HTTP information to the client, and the client can then establish a connection that way. I don't know if I think by default it's just going to be on. I don't know if there's going to be a way to disable it if you want to just run RPC over HTTP. There might be scenarios where a customer is using certain devices that are already in place, and maybe MapiHttp isn't compatible with those. So there probably might need to provide a way to disable it.